Hello everyone, welcome to SPSVERSITY. So today we are going to see the Kinetics Part 2. I am here, your educator from SPSVERSITY. If you like the videos, please click the like button and subscribe to the videos. So here we go. In the previous class, I hope you all remember where we stopped. So it's about the order, molecularity, in the rate of the reactions. That's where we stopped, and I'm continuing from that. So here we are going to see the integrated rate equations, or the expressions for the rate constant in case of zero order and in case of first order reactions, which is mentioned in the NCERT textbook, which are very important. So we'll go ahead with the zero order reaction first. What exactly is a zero order reaction? In the previous class, we spoke about the order of the reaction, isn't it? So the zero order reaction. Zero order reaction is one where rate is independent on the concentration of the reactant. That means if you have any reaction, reactant gives rise to product. Rate is directly proportional to the concentration of the reactant to the power 0. This is the order. Or rate is equal to K into concentration of the reactant to the power 0. Okay. So that means the rate is apparently independent of the reactant concentration. The rates of the zero order reaction we are going to see, and that means if you increase or if you decrease the concentration of the reactant, that's not going to have any effect on the rate. That's how you get this one. Can you see the rate versus time? It's a straight line for a zero order reaction. Okay, and here anything to the power 0 is equal to 1, so that rate becomes equal to rate constant. So both the rate and the rate constant are going to have the same units, and those are, so d, how do you define rate as? Change in the concentration, that's dr divided by dt. So what's the unit for the concentration of the reactant? It's mole per liter, divided by the time, that's second. So it's mole per liter per second, both for the rate as well as for the rate constants. We have some examples of zero order reactions. What are those? Almost all the reactions which happen over the surface of the catalyst, they are considered as zero order reactions. So hydrogen and the chlorine, they combine in the presence of radiation to produce HCl, or the decomposition of ammonia on the surface of molybdenum to produce nitrogen and hydrogen. All these are examples for the zero order reactions. So what are we going to do now here? So if we are going to derive, so rate is equal to K into concentration of the reactant to the power 0. Or I can always write dr by dt. Rate is change in the concentration with respect to time, which is equal to K into concentration of the reactant is r to the power 0 is equal to 1. Always the concentration of the reactant decreases, so you have to put a minus sign over here. Now we'll rearrange this expression. We'll take this dt here and we'll shift the minus symbol here. So what's that you are going to get? dr, which is equal to minus k dt. So there are differential terms, dr and dt. Now you have to integrate to get their whole values. Okay, if you integrate them, the k is a constant, so we are keeping it outside. So it becomes r, which is equal to minus k, integration of dt becomes equal to t plus the integration constant I. You can use the integration constant as I, you can use the integration constant as C according to your convenience. But there should be some meaning. You can't use all of a sudden, you can't bring x and add it. You can use either the constant as C or the constant as I. So this is the concentration of the reactant at time t. Time is equal to t. Now I'm sorry. Hello, sorry for the technical glitch. I had to. Yeah, here we go. So from here, if we move, the concentration of the reactant is at time t, that's called as R. If the time is at t, that means you are starting a reaction. So when the time is equal to t, or time t is equal to 0, that's the beginning of the reaction. The reactant concentration will be R naught. Okay, so we'll apply this to this particular equation. So when time t is equal to 0, this whole term disappears. You have 0 plus I, which is equal to the concentration will be initial concentration. So you got the value of I, isn't it? I is equal to R naught. You put that here. So you get the equation R is equal to minus kT plus R naught. Now you rearrange this expression, you get kT, which is equal to R naught minus R, or K is equal to R naught minus R divided by T. This is the expression for this rate constant in case of zero order reactions, where K is the rate constant, R naught is the initial concentration of the reactant, R is the concentration of the reactant at time is equal to T, and the T which is in the denominator is the time. Now we have, if you have to draw a graph of this, this is in the form y is equal to mx plus c. So along the y-axis you are going to take the concentration of the reactant, along the x-axis you are going to take the time. If you plot a graph, here it is mentioned as a naught a, if you plot a graph of that, so this will be the concentration of the reactant divided by time, and this will be the descending type graph, because the slope of this particular line is minus k. So since it's the negative, you have to draw a descending type of graph, and the intercept of this is the initial concentration of the reactant, that's A naught or the R naught. Then you have a term called as half-life. Half-life is the time in which the concentration of the reactant reduces exactly half to the initial value. So if you take 100 molecules of the reactant, or a 1 molar concentration of the reactant, to decrease it to 0.5 molar, that's half, exactly half of that, what is the time taken? That's called as T half. Now we'll apply the conditions to this equation. So we have K is equal to R naught. I'm taking it from the previous expression which we just derived now. We'll rearrange this for T. Now when time is equal to T half, when T is equal to T half, what is R, or what is R naught? The initial concentration will not change, but the concentration of R is equal to R naught by 2. It exactly reduces to half of the initial concentration. So this becomes R naught minus R naught by 2 whole thing divided by K. Now if you rearrange it, I have T half is equal to 2 R naught minus R naught, that is nothing but R naught. This 2 we are going to take it to the denominator. So T half is equal to R naught divided by 2K. So T half depends on the reactant, initial concentration of the reactant over here. Hope you get it. This is about the zero order reaction. So both the expressions you keep it in mind. So we have a question over here. Using the integrated form of the rate law, determine the rate constant K. They have asked you to determine the rate constant K of a zero order reaction. If the initial concentration they have given of a reactant, that's A, is 1.5 molar, and after 120 seconds, the time they have given, the concentration of A is 0.75 molar, and you have to determine the half-life as well. So we'll start with the expression for K. K is equal to initial concentration minus the concentration at time is equal to T divided by the time. So they have given the initial concentration, that's 1.5 molar, and after 120 seconds, the time is in seconds, it decreases to 0.75 molar. So 1.5 minus 0.75 will be 0.75 divided by 120. This is what you are supposed to do now. So if you divide it, that's a 0.75 divided by 120, that's going to give you the answer as 0.00625. And this is a concentration, this is molar per second, or you can even put it as mole per dm³ per second. That also works. And what is the half-life of the substance if the original concentration is 1.2 molar? So they have given you the R0 value, which is 1.2 molar. What you are supposed to find out? Half-life of the substance. So T half is equal to initial concentration divided by 2K. And R0 is 1.2 divided by 2 times K is 0.00625. If you do that, you're going to get 1.2 divided by 2, whole thing divided by 0.00625. That's going to give you the T half as 96. And since this is molar, this is molar per second, they get cancelled and the second goes to the denominator, so it becomes 96 seconds. Okay, depending on the unit, if you are going to keep it in minute, you have to take it as minute. If you are going to keep it in seconds or hours, depending on that, you are going to apply the units. Now we'll go for the first order reaction. What exactly is a first order reaction? The first order reaction is one where you have a reaction, that's reactants give rise to product. Then the rate is equal to, or rate is directly proportional to the concentration of the reactant to the power 1, or rate is equal to rate constant into the concentration of the reactant to the power 1. So the order 1, if the order is equal to 1, then it is called as first order reaction. That means the rate depends linearly on one of the reactant concentration, only one. So if you have a reaction, A gives rise to product, then the rate of the reaction is directly proportional to the concentration of that particular reactant. If you have two molecules of A, then also rate of the reaction directly depends on the concentration of A. If you have two reactants, then the rate of the reaction depends on only one of these, not the other. So you have to take that in the excess or any under some reaction conditions. The rate of the reaction depends on only the concentration of one of the reactant. Hope you get it. Then example, all the radioactive decay, they follow the first order kinetics. Then the hydrolysis of this sucrose and the hydrolysis of esters, decomposition of hydrogen peroxide in the aqueous solutions, all of this follow the first order reaction. Let us calculate, let us solve let us find out an equation for the rate constant of first order reaction. So how do we start? Consider a reaction, reactants give rise to product. We write rate is equal to K into concentration of R to the power 1, which is nothing but R. You can take it as A also. Rate is equal to minus dR by dt, which is equal to K into R. Now we'll put R terms together and the other terms together. We'll take the minus sign this side. So we have dR divided by R, which is equal to minus K dt. Now you have to integrate to get this. The K will be outside because it's a constant. You are integrating only the differential terms. So dR by R is nothing but minus ln R, which is equal to minus K T plus I. Okay. What is the integration of dr by r? Is it ln r or minus ln r? So this kind of things you should be very clear with. Is it minus r? If you are watching, I'm expecting an answer. What is that? Is it minus or is it plus? Okay, no answer at all. I'll take it as plus. Kt plus I. Now integration of 1 over x is ln x, and this is time at time is equal to t. Now let us find out what is I. How do you find out? When the time is t is equal to 0, this term becomes 0. So this becomes ln r naught, which is equal to I. We'll apply this over here. Ln r, which is equal to minus kt plus ln r naught. If you're going to draw a graph of this, that's y is equal to mx plus c, then the slope would be minus k. Along the x-axis you take t, along the y-axis you take ln r, and the intercept of that will be, see here it is. And how do you get this? Let me rearrange the equation. I'm doing it as a part. Kt is equal to ln r naught divided by r. Ln r naught by r becomes e to the power kt. So you should know, or e to the power minus kt. You should know how to rearrange this expression. Okay, let's move ahead. Now, what is the next part? Rearrange this. Kt is equal to ln of r naught minus ln r. Ln a minus b is equal to ln ab, or kt is equal to ln of r naught divided by r. These are the concentration terms. I'll use this bracket. When you convert this into log term, kt is equal to log r naught divided by r into 2.303. Now you write the expression for k. K is equal to 2.303 divided by T log of the initial concentration divided by the final concentration. That's the concentration at time is equal to T. This will be the expression to determine the rate constant of first order reaction. Okay, so keeping this in mind, you can have different graphs for this. The concentration varies linearly, or the ln A versus this one time. This is ln A naught. So you get this type of graphs for the first order reactions. Now, if you have to find out the half-life, we have discussed half-life is the time in which the initial concentration of the the reactant that reduces to exactly half. That's called as T half. So we have the expression and we rearrange the expression as T is equal to 2.303 divided by K log of R naught divided by R. Okay, when time t is equal to t half, which is equal to 2.303 divided by k log of r naught divided by r naught by 2. In the place of r, because at time t is equal to t half, r becomes equal to r naught by 2. R naught get cancelled. This 2 goes to the numerator. So you get t half is equal to 2.303 divided by k log 2. Log 2 is nothing but 0.3010. When you multiply this, I'll keep it as it is 0.3010 into 0.2.303 divided by k. This is nothing but t half is equal to 0.693 divided by k. So here in the expression, t half is independent on the concentration, any of the concentration of the reactant. So this is the expression for t half in case of first order reactions. Okay, so remembering these two, we are going to solve this question. A 3 gram of a substance, so the A decomposes for 36 minutes and the mass of the unreacted A remaining is found to be 0.375. So you start with the initial concentration, which is 3.0 gram. And the time they have given 36 minutes. After 36 minutes, the mass of the unreacted A remaining, it is remaining. So the concentration at time t is 0.375. What is a half-life? We have the expression for half-life. T half is equal to 0.693 divided by K. To find out T half, since it's a first order, they have mentioned you have to see the order as well, the first order. So in case, if you change it, T half is equal to 0.693 divided by K. If you need K, sorry, T half, you need K. How do you find out K? K is equal to 2.303 divided by time log of initial concentration divided by the final concentration. That's 2.303. If you want to convert the time into seconds, you can convert. I'll keep it as in minutes. Log of 3 divided by 0.375. So in case, if you can roughly take it as log 10, then it is going to become 1. Okay, if you want the exact value, you can use your log table or the calculator, but in the competitive exams they are going to give almost the values like log 10, log 10 to the power, those values. But in case if you need the exact value, you can calculate that also. So the log of 3 divided by 0.375 is going to give you 0.90. I'll take that value as it is. 2.303 multiplied by 0.90 divided by 36. Okay, 2.303 into 0.90 is going to give you 2.07 value, divided by the 36 is going to give you 0.057. See the units in the numerator. In the numerator you have the concentration terms and the units get cancelled, so you have the unit as per minute because this is the only one unit which you have over here. Then you divide that 0.693 divided by 0.057, so it would be so that will come out as 12.15 minutes. Hope you get it. So to calculate the t half, you need the k value. So you find out k first, then you substitute and get the value. So in case of first order reaction, the k rate constant is going to have the unit as per second or per minute or per hour. Then how is the rate law related to the mechanism, or how you are going to relate the order with the mechanism of that reaction? This is what you have to see now. So let's consider any reaction for that matter. If this is the reaction, 2NO plus 2H2 is going to give you 2 rate is directly proportional to NO to the power 2 and H2 to the power 2. When you see this equation, if this is not the experimentally determined one, you get this as this just by looking at this. You write rate is directly proportional to NO2 to the power 2 and H2 to the power 2. How do you write it? That is depending on the equation. But when it is done in the lab, this is the theoretical one. And if you are going to do it in the lab, you're going to get rate is directly proportional to NO to the power 2, H2 to the power 1. So 2 plus 1, that gives you the order of the reaction. That's nothing but 3. So you can tell us this follows the third order kinetics. But if you write the reaction, so if you write the rate of the reaction, if you follow the steps, so in the first step, if you see the mechanism of the reaction, in the first step, two NO molecules combine to give N2O2. This is the first step. And this is a fast and reversible reaction. Then the step 2, this N2O2 is going to combine with just one molecule of H2, and this gives you N2O plus H2O. This is a slow step. And in the step 3, what is that you're going to get? This N2O is going to react with one more molecule of H2, and that gives you N2 plus H2O. This is again a fast step. So whenever you say the order of the reaction, in case of complex reaction, this is not a single step reaction, it's a complicated one. It takes place in 3 different steps. So from this reaction, you are going to measure the order of the reaction. This is how you calculate the order from the slowest step. So the rate of overall reaction is rate of step 2. So you write rate is equal to K into, we'll consider this step 2. I'll change the ink. So for step 2, you write rate is equal to concentration of N2O2 into H2. Hope you get it. Now, The concentration of the intermediate you can get from other steps. So generally, whenever you say this, because there is a reversible reaction as well, because of which if you write the Kc, that is going to be N2O2 for this particular step, this one. For N2O2, this is NO to the power 2. Okay, in the place of N2O2, because we don't have that term in the main expression, but we have NO in the main expression, so we have to put this N2O2 in terms of NO. This is a fast and reversible reaction. From this we have the equilibrium constant Kc is equal to concentration of the reactant, sorry, product over the concentration of the reactant. Now if you multiply Kc with NO, you get the concentration of N2O2. So after this, rate is equal to K into Kc into NO to the power 2 into H2, or the rate is equal to 2 multiplication of 2 constant is going to give you a constant itself, NO2 to the power 2 into the concentration of H2. So though the reaction appears to be following the fourth order kinetics, when you write the reaction, that is going to have a different steps, and from this lowest step you are going to see the order of the reactions, and as well when you calculate the rate you are going to put an intermediate, because it is a slowest step. In that slowest step the rate is equal to concentration of the reactant, that is directly proportional. So rate is equal to K into concentration of N2O2 into concentration of H2. But N2O2 is an intermediate species, so you have to express into the concentration in terms of NO. So what you are going to do, you are going to take N2O2 in terms of some other reactants which appear in the main equation. So how do you do that? You take the Kc value and you are going to put the values over there, and at the end you get rate is equal to K into NO to the power 2 and H2. So the theory, if the final order will be 3. So this is how the rate law is related to the mechanism of the reaction. Then you have the pseudo first order reaction. What exactly pseudo first order reactions are? Whenever you say pseudo, it is not true or false. First order reactions. These reactions are the reactions which follow the higher order but are made to follow the first order kinetics under some reaction conditions. Okay, just like you are hungry, but you say, you deny it saying I'm not hungry, just to keep yourself ashamed from anyone. Say you attend a function and you attend or you go to someone's place who is not so close to you. What do you say? No, I am not hungry. They are going to call you for lunch and you are going to say, no, I'm not hungry, I've just eaten. Depending on the reaction conditions or depending on the situations you are going to react, right? The same way, these are the reactions which are not of first order but follow the first order kinetics. So how is this going to happen? You take the reaction, the hydrolysis here, it is the inversion of cane sugar. Cane sugar is nothing but sucrose over here. Or you can even take the hydrolysis of ester. If you see the reaction, there are two reactants. So how do you put the rate as? Rate is equal to K into concentration of cane sugar into concentration of water. So the rate should depend on the concentration of cane sugar as well as water. If you increase any one of the concentration or both the concentration of these reactants, the rate should increase. But what happens is, since you have taken water in the excess, in this particular reaction water is taken in excess, because of which its concentration almost remains the constant throughout the reaction. So if the concentration of this remains constant, so the rate won't be affected by changing the concentration of that. So you write rate is equal to K into concentration of cane sugar and this power 0, because the rate is independent on the concentration of water. So rate is equal to K into concentration of cane sugar only. So this follows the first order kinetics to the power. If there is nothing in the power, you have to take it as power 1. So rate is directly proportional to concentration of just one of the reactants among these two reactants. So these are called as pseudo first order reactions. Okay, so we'll proceed with the next one. Hope I'm very clear here. Yeah, I'll just see. I just want to see if you are watching. Okay, that's cool. If anyone is watching, please like and put a subscribe button, press on the subscribe icon. That will really help us to grow and give you the good contents here. Yeah, we shall move forward now. Yes, so we are going here. Mm, I'm just checking if anyone is watching over here. Yes, I got the link. Next one. The next one is about the catalyst. Whenever you say the catalyst, it is a substance. Generally, whenever you say catalyst, it is added to increase the speed of the reaction. That is going to have enormous effect on the speed of the reactions, like the rate of the reaction. But still, we have two catalysts. One is the positive catalyst, and the one is the negative catalyst. The positive catalyst is the one which is going to accelerate the reaction. That means it is going to increase the speed of the reaction, just like you put an accelerator in your car. So that increases speed. The negative catalyst is the one which is going to hinder the speed, that is going to make the reaction slow, which is called as inhibitor or the negative catalyst. Just like you apply a brake, so the reaction is going to be very slower. Okay. Now there are two different type of catalysis. One is the homogeneous, the other one is heterogeneous. This we already discussed in the surface chemistry chapter. So the homogeneous catalysis is the one in which the catalyst and the reactions are reactant molecules are in the same phase. For example, uh, the sulfur dioxide and the oxygen, they combine to give SO3. There can be different catalysts depending on that. V2O5 or NO. You can take this. SO2 plus O2 gives you SO3. Consider this reaction in both the cases. If it is a heterogeneous, this is a gas, this is a gas. These are the reactants are in the gaseous phase. And if it is a homogeneous catalysis, you have to take the reactants. That's these are the reactants and the catalyst. That's NO, nitric oxide. This is also in the gaseous phase. This is easy because all are in the gaseous phase. They intermix well with each other. And this is on the surface of a catalyst V2O5, which is vanadium pentoxide, is a solid. So here the reactants and the catalyst are in the different phase. This is what is meant by heterogeneous catalysis. Now we'll go to the Arrhenius theory. So this particular theory explains in a particular reaction, how do you draw the energy profile diagrams and what exactly are some terms and how the rate is going to be affected by the temperature. So we are done with the effect of concentration until now. And the effect of catalyst and the effect of temperature is what we are going to see now from here. From the previous studies, we know that the rate is directly proportional to the concentration of the reactant. So with increase in the concentration of the reactant, the rate of the reaction is going to increase. Now when we come to Arrhenius theory, Arrhenius was a scientist who gave a theory which says the effect of temperature as well as the effect of catalyst on the rate of the reactions. So let us consider a reaction. Reactants give rise to product. How do you draw the energy profile diagram? So this one. I'm just putting 1020 just to make you understand. That doesn't mean these are the exact values. And here also I'm putting 1020. What should I take on the x-axis and what should I take on the y-axis? Here I'm taking the energy along the y-axis, and along the x-axis I'm going to take the reaction progress, how the reaction is going to proceed. Okay, now say the reactant molecules have 20 joules of energy. I'm changing the ink. So the reactant molecules have 20 joules of energy and the product molecules have about 40 joules of energy. I'll start with the reactant molecules. The reactant molecules are over here. This is the energy of the reactant molecules. And at the end, you have the product molecules with 40 joules of energy. I'm writing it here. So the generally reaction will not proceed from reactants to products directly. Just like you are in the grade 8 and you are going to grade 9, or you are in the 12th grade and you are going to just you are going to enter the medicine or the engineering field, you directly don't go, right? You have to cross so many barriers, so many hurdles. You have to put the effort. The same way, this will be the reaction profile. So I'll extend the graph and say this is 70 and this is 80. Now what is 20? Here 20 is the energy of reactants. Can you see that? It's the energy of the reactants. And now What is the height? So this much amount of energy. This is the energy of the reactant, and this is the peak, which is 80 joules. This is called as threshold energy. So this is the minimum marks you have to get to pass the entrance exam. So this is 80 joules. You are at 20 level, you are just scoring 20 marks in your regular exams, and to get the pass marks in your competitive exam, you have to score 80. From where you are going to get 80? How do you get this 60 gap? How is this 60 gap is going to be filled? You are going to put the efforts. The teacher is going to scold you, and teacher is going to continuously give you the assignments, and your parents are going to pressurize you. Because of that, you gain 60 joules of energy. So this is what is happening. The reactant molecules will have some amount of energy, and they are provided with some amount of energy which is given from outside, which is called as activation energy. So what is activation energy? It is the extra energy which must be possessed by the reactant molecule so that the collision happens. So if this particular energy is not given, then the reactant molecules cannot form the product. So you are one side of the hill. Unless you reach the top, you can't go to the other side of the hill. So you have to go to the other side of the hill. How do? You just climb it. To climb, you need to have some amount of energy, isn't it? So that particular amount of energy, which is provided by outside, when you climb, what you take so many dry fruits, you take water, you take food, and you have pre-planned exercises and all before you climb. All this will give you the activation energy. So this is equal to the threshold energy. Et is the threshold energy. Er is the amount of energy provided by the which is there in the reactants. Ea is the activation energy. Now this gap between the energy of the reactants and the energy of the product, that's 20 joules. So the reactant molecules have 20 joules of the energy, product have 40 joules of energy. This much amount of energy is going to be taken in. So this is endothermic reaction. If the profile is reverse, reactants have more energy and the products have less energy, then the energy will be given out, which is called as exothermic reaction. So I think you are very clear with the threshold energy, you're very clear with the activation energy, and the possessed by the reactant molecules. You have some amount of energy, that's your energy. And to pass, you need to cross certain barrier. That peak is called as threshold energy. Only if you reach that peak, you can get the next grade. So that extra amount of energy which has to be provided from outside, that's called as activation energy. Okay? Yeah. So we have something related to the activation energy, which is Arrhenius equation. According to Arrhenius, K is equal to A into e to the power minus EA by RT, where K over here, if you can see here, K is the rate constant. A is called as frequency factor or pre-exponential factor, or it is also called as Arrhenius factor. And minus EA. EA is the activation energy. R is the gas constant. T is the temperature. And this term, e to the power minus EA by RT, that's called as Boltzmann factor. Now, you can see the relationship between temperature and the rate constant over here in this particular slide. Then, what will happen if you increase the temperature? And all these studies we are going to do in the next class. Okay, so, but we'll see what happens if you have the catalyst in the reaction. Say you have a catalyst in the reaction. Generally, the reactants react to give the products. And this reaction is very slow. So we'll draw the graph. So this is a graph. Okay. What is activation energy? This one. From the energy of the reactant molecules to the peak. So this is the activation energy. On the y-axis, you are taking energy. On the x-axis, you are going to take the reaction progress. This is in the absence of the catalyst. If the catalyst is not there. When you add the catalyst, what should happen? There will be an intermediate complex formed between the reactants and the catalyst, and this will be the path now. So this becomes the activation energy. Now, this is in the presence of catalyst. What difference you see over here? So addition of the catalyst is going to lower the activation energy. I think it's clear to you. And just like if it is a very big hill, if it is difficult for you to climb, then you are going to through a shorter hill, like where you can climb depending on your energy. So the addition of the catalyst is going to lower the activation energy, more molecules. So in case if the exam mark is if the passing mark is decreased from 40 to 20, there will be many students who are going to cross that barrier, isn't it? The same way, the greater is the energy gap, less molecules will be crossing that barrier. So the catalyst, if you add, the activation energy or the peak of that is going to decrease, more molecules will have that particular amount of energy and they can form the product. So more will be the rate of the reaction. This is how the catalyst is going to affect the rate of the reaction by providing an alternate path of lower activation energy. This is like a shortcut. So we have certain questions over here which we can solve one after the other. So what do you think about it? The reaction which is a first order, so they have given the reaction is of first order. With respect to a reactant A, has a rate constant 6 per minute. If we start with 0.5 mole per liter per A and if the concentration decreases to 0.05 mole per liter, what will be the time required for this change in concentration? So how are we going to solve this? So what is given? So the rate constant they have given 6.0 per minute, and the initial concentration of that you have started with 0.5 mole per liter, and the final concentration at time t, that would be 0.05 mole per liter, and you have to find out what is the time taken for this change. So you have the expression for first order kinetics. They have given it as it follows the first order kinetics. If they have not given, see the rate unit of rate constant, it is per minute. Again, it should be a first order. So K is equal to 2.303 divided by T log of concentration, initial concentration divided by concentration at time t. You rearrange this, t is equal to 2.303 divided by 6 because k is equal to 6 log of the concentration, that's 0.5 divided by 0.05. This is log 10. Log 10 is nothing but 1. So t is equal to 2.303 divided by 6. 6 ones are 6, almost 3s are 24. So it is approximately around 0.38. So this is per minute. When it goes to numerator, it is going to become the minute. So the correct answer for this particular question will be option A, 0.384 minutes. Okay, we'll go to the next question. Our first order reaction is 20% completed in 10 minutes. Calculate the time taken for the reaction to go for 80% completion. How are you going to solve this? If you're watching this, you can go put it in the comment section, say what is going to happen. So what do you think the answer is? How do you solve this? Say, what you have to do, calculate the time taken for to go to 80% completion. So you have to start with determination of rate constant 2.303 divided by 10, 20% completed. What do you mean by 20% completed? Initially it was 100. Whenever the percentage is given, you have to take it as initially it was 100. 20% completed in the sense the remaining is 80. So it is 0.2303 log of 100 by 80. You can calculate that in case if you have, but generally in the examination they'll be providing this. So log of 100 divided by 80 is going to give you 0.0969 or 0.97. This multiplied by 0.2303, that is going to give you 0.22. Okay, unit. So this is 10 minutes. So this becomes per minute. Calculate the time taken for 80% completion. So 2.303 divided by the rate constant, that's 0.022. Okay, log of 100. So 100, and again the initial concentration is 100 for 80% completion. That means you are remaining with the 20%. Okay, what is log? Log 100 by 20 is going to give you 0.69. That's 6989. And what is t 2.303 divided by 0.022? It is approximately equal to 100, or you can take it as 100.4. So this one multiplied by 0.69 is going to give you almost 72 minutes. So be careful when you convert the unit terms. That's minutes and seconds. So the next question is, which among the following is a false statement? Molecularity of a reaction is 0 or a fraction. Then for a first order reaction, T half is equal to 0.693 divided by K. The rate of zero order reaction is independent on the initial concentration of the reactant. Half-life of a third order reaction is inversely proportional to square of the initial concentration of the reactant. So how do you do this? Molecularity, which is a false statement, you should make a note of this first. What do you mean by false and what is true? That you have to see. Sometimes you select a wrong statement, and you sometimes the question will be identify this a true statement. Okay, molecularity of a reaction may be 0 or fraction. It cannot be 0. Any reactant cannot have a fraction. This should be, the molecule should be complete. It cannot be 0. If in a reaction, if the number of reacting molecules is 0, the reaction itself cannot happen. We'll see the other answers also, because if it is a JE question, then you may have more than one right choices. So now this is a false statement. For a first order reaction, T half is equal to 0.693 divided by K. We have found at it. Rate of zero order reaction is independent on the initial concentration, right? Half-life of a third order reaction is inversely proportional. Yes, T half is inversely proportional to the reactant concentration to the power 2. So this is also true. The wrong statement or the false statement is just the first one. A reaction which involves two different reactants can never be. If there are two reactant molecules, it can follow, say, this is a reaction. A plus B gives rise to product. How do you write rate? Rate is equal to concentration of A into concentration of B. In case if it is pseudo first order, or if any other reaction conditions are applied, or if the rate depends on only one of the concentration, then order can be 1. It can be a first order reaction. It can be unimolecular. It can be second order reaction. So if both are participating, then order can also be equal to 2. It is bimolecular because there are two reactants reacting. It cannot be unimolecular. So different reactants they have mentioned. If there are two different reactants, it cannot be unimolecular reaction. Uni in the sense one. There are two different reactants, and uni in the sense there is just one. So it cannot be unimolecular. 3A gives rise to B plus C. It would be a zero order reaction. The rate of the reaction is proportional to square of concentration of A. The rate of the reaction remains same at any concentration of A. The rate remains unchanged at any concentration of B and C. The rate of the reaction doubles if the concentration of B is increased to double. A zero order reaction is 1. However you change the concentration of the reactant, the rate is going to be unaffected. So rate is independent on the concentration of the reactant. So the rate of the reaction remains same at any concentration of A would be the right answer. The unit of rate constant for a zero order reaction. So how do you find out the rate constant unit? Rate constant is equal to, or we start with the rate. Rate is equal to change in concentration over time. Rate is, what is rate? How do you find out rate? Oh, okay, wait, let me change the expression. Yeah, so you have to find the unit of rate constant. We have rate is equal to K into concentration of the reactant, or rate is change in concentration divided by time, which is equal to K into concentration. If you want the unit of rate constant, then you have to rearrange. Here it is concentration divided by time. You bring this concentration term to the denominator. So if it is zero order reaction, this becomes power zero. So anything to the power 0 is equal to 1. The unit will be concentration divided by time. So what is the unit of concentration divided by time? The unit of concentration is mole per liter divided by second. So it is mole per liter per second. That would be the right answer. So this is all about the kinetics part 2 in today's session. In the next class, we are going to see how the temperature is going to affect the rate of the reaction, and we are going to solve a couple of problems which are from NEET and the JEE, and as well as we are going to solve some of the problems which are in the textbook. So until then, keep revising the topics and put your comments below. These are very, very precious for the SPSVERSITY to grow and also to get you the quality